In this lecture, we are going to discuss about interrupts in 8086 microprocessor. So, what is an interrupt? So, interrupt is nothing but breaking normal sequence of program execution, breaking normal sequence, right. So, while CPU is executing a program, an interrupt break the normal sequence of execution of instructions, diverts its or transfers the program control to some other program called interrupt service routine. So, ISR. So, the ISR is a program which serves the interrupt request. After serving the interrupt, that is after executing interrupt service routine program, the control is transferred back again to the main program. So, whenever number of devices interrupt a CPU at a time, and if the processor is able to handle them properly, it is said to have multiple interrupt processing capability. So, it is also there in 8086. So, 8086 has two hardware interrupt pins, that is NMI, non-maskable interrupt, and INTR, interrupt request. These two are the interrupt pins available in 8086 microprocessor. So, among these two, non-maskable interrupt having highest priority than interrupt request, INTR pin. So, NMI, this is non-maskable. So, that means non-maskable means the interrupt occurs through this pin is served by the microprocessor. It cannot mask. Now, masking is not possible, or that is disabled. We cannot disable. But INTR, interrupt request pin, is a maskable interrupt. So, we can mask by using a flag is there in 8086, interrupt flag. So, by using interrupt flag, we can mask this INTR pin. That means, we can enable or disable INTR pin by using interrupt flag, IF flag in flag register. So, this INTR is a 256 types interrupts are there. So, coming to this, the INTR types, the 256, the value in hexadecimal, it is ranging from 00 to FH. If more than one type of INTR interrupt occurs at a time, then an external chip called programmable interrupt controller is required to handle them. So, coming to the types of interrupts in 8086. So, there are two types. Number one is external interrupt. So, why this occurs? Due to an external device or a signal interrupts the processor. That means, by applying an external signal to NMI or INTR pin, interrupt will be occurred. That interrupt is called external interrupt. Next one, this is example keyboard or mouse. We can mouse also is an example for the external interrupt. And second one is internal interrupts. The interrupts generated internally by the processor circuit or by execution of an interrupt instruction, that is INT instruction, that is called internal interrupts. So, example divide by 0, overflow interrupts, interrupts due to the INT instruction. These are the examples of internal interrupts. So, two types, internal interrupts and external interrupts. So, the processing of interrupts, coming to the processing, for example, while this is the main program, at present the microprocessor is executing this main program. So, during the execution of the program, an interrupt occurred. In 8086, the address of instruction is stored or pointed by two registers, that is code segment register and IP, because the instructions, the programs all are stored in code segments. So, that is why we need the code segment will register will point to base of the code segment, and IP will point the particular memory location in the code segment. That is why here when the microprocessor is executing the program, an interrupt is occurred, that particular address, the address of instruction when the interrupt is occurred is stored in code segment register and IP, instruction pointer register. So, now what the microprocessor it does? So, it executes the current instruction, then it pushes the flag PSW, program status word, in stack segment, and it pushes also the CS value and IP value. Afterwards, it fetches the address of interrupt service routine program. That address is available in interrupt vector table. There is a table is there which consists of all the addresses of the 256 interrupts, that is 256 ISRs. So, it will fetch that address and load the CS and IP values to the registers, then it starts executing interrupt service routine. Okay. At the end, coming to at the end, we have a instruction we are going to use at the instruction RETI. This instruction transfers the program control from interrupt service routine to the main program where it was interrupted. So, while coming back, the processor needs the status and address of the main program where it was interrupted to resume that one. So, that is why the microprocessor pops the contents of IP from the stack and CS, then we will get the address of the main program, and then it pops program status word flag register from the stack, then it can understand, it knows the status of the main program and starts the execution from here onwards till the end of the main program. That is the processing of interrupt in 8086. So, processing of interrupt in 8086, how? This is we call it as interrupt cycle of 8086. When an external device interrupts the CPU at NMI or INTR pin while executing a program, the CPU first completes the execution of the current instruction and IP is incremented to point the next instruction. It always points the address of next instruction to be fetched, which one? IP, instruction point register. So, the contents of IP and CS are pushed down to the stack, even program status word also. So, the CPU then only acknowledge the requesting device immediately on INTA if it is a NMI or a trap or a divide by 0. If it is a NMI request, the CPU checks IF interrupt flag status, because by using interrupt flag we can disable or enable INTR a pin. So, if INTR IFE flag is set, then it acknowledges the device, otherwise the interrupt is ignored. So, after acknowledgement, the CPU computes the vector address from the type of interrupt, then the control is transferred to ISR for serving the interrupt device. So, the ISR address is available in interrupt vector table. So, at the end of ISR, last instruction should be IRET. So, this is the interrupt cycle or processing of interrupt in 8086 microprocessor. So, you see interrupt response sequence, what is going to happen. So, this is main, the main program status word, flag register contents, that is this will be stored in the stack segment. So, stack segment SS and SP is the stack pointer points the address in a stack segment. So, first flag when interrupt occurs, the flag register contents will be stored in here in the stack, and SP will be whenever push operation is performed, the stack pointer will be decremented by 2 in 8086. So, it will be decremented by 2. So, in that location main program base address, which is in a code segment register, will be stored, and then SP is decremented by again 2, then the contents of instruction pointer is stored in stack. This is the order. And then what is going to happen? Then it fetches the address of interrupt service routine ISR from interrupt vector table. Then it will be loaded into this one, ISR, CS and ISR IP. So then it starts executing ISR, interrupt service routine. So at the end of ISR, what we have? We have a IRET instruction. After executing IRET instruction, then what is going to happen? Here it will fetch, this is ISR CS and ISR CP for example. Then it starts, it's going to, the control will be transferred to back to the main program after executing the interrupt service routine. So this is just a response. For example, the microprocessor, as we discussed in the first slide, multiple interrupts occurred. What is going to happen? For example, this is a main program. We have interrupts, 256 interrupts, that is from 00 to FFH. For example, INTA 0A is occurred. While executing the INT 0A, immediately another interrupt occurred. Another interrupt, there is another interrupt occurred. What happened? Then again, that means while executing 0A, then what is 0B occurred? Then the microprocessor suspends execution of ISR 0A and it is going to, the control will be transferred to ISR of 0B, like that. This is, we call it as nested interrupt. That means the interrupt occurs while executing the another interrupt, that is nested interrupts. Coming to the interrupt vector table, right? Interrupt vector means if any interrupt occurs, then the microprocessor suspends the program execution and transfers the control from main program to interrupt service routine. So to transfer that control, the microprocessor needs address of interrupt service routine program. Okay, the address of interrupt service routine program is stored in a table. That means it is a memory. That is, we call it as interrupt vector table, because we call it as interrupt vector. So each ISR, interrupt service routine program, having two addresses, that is base address and its offset. That's why we call it as interrupt vector, right? So when the interrupt enabled, IP onto the stack, we already discussed about this interrupt vector. This is interrupt vector for each and every interrupt service routine program having address IP and CS, which requires to store the contents of CS IP. That means address, it requires 4 locations. That's why it is from 000 and 1 for IP, 2 and 3 for CS. Okay, so it is a memory block which contains address of ISR. The size of interrupt vector is 4 bytes to store CS and IP. And now interrupt, this is only one interrupt vector. Interrupt vector table consists of this much vectors, right? This is, for example, this is the interrupt vector table. This is first vector, second, like this, from type 0 to type 225. Okay, so it is a memory block which contains interrupt vectors. Since there are 256 types of interrupts, there are 256 interrupt vectors. Hence, the size of interrupt vector table is 4. For one vector requires 4 locations into 256 interrupts, that is 1024 kilobytes, right? That is 1 KB size. It is reserved, right? This is look like. So out of here you can see all the interrupts, each and every interrupt type having address, that is CS value and IP value, like this. So these 256 interrupts are divided into from 0 to 255, that is 256, 3 types, dedicated, reserved, available interrupts, like this. So, in 8086 system, the first 1 KB memory from 000H to 003FFH, that is 1 kilobyte, is, if we convert 1024 into hexadecimal, we will get 003FFH, is reserved for storing the starting address of ISR. This block of memory is called interrupt vector table, right. So, the interrupt vector table contains 256 interrupt vectors. The interrupt vector contains address of ISR, IP and CS values of ISR address. For example, the interrupt vector address can be calculated by multiplying the type with 4, because each and every type requires 4 memory locations. For example, type 2 interrupt. So, what is 2 into 4? 8. This is the address of ISR, that is interrupt type 2. Okay. For example, there are 3 sources of interrupts: signal applied to NMI, NTR pins, and the software interrupt by executing INT instruction, error execution, divide, overflow. And so the use of the 8086 uses 26 types of interrupts, and they are categorized into 3: dedicated interrupts, reserved interrupts, available interrupts. So, dedicated interrupts are 5: divide by 0 and single step interrupt, non-maskable interrupt, type 3 breakpoint, type 4 overflow interrupt. So, among 5 interrupts, divide by 0 interrupt having highest priority has type 0 has highest priority among all the interrupts of 8086 microprocessor. So, this is about interrupts of 8086 and interrupt response and interrupt cycle and interrupt vector table, right. Thank you.